It's the weekend, so today we are going to solve this problem. Its rating is 2100 and is posted by Ford, right? So as always, we are going to introduce this problem by explaining the example here, right? So the input has two numbers. The first is 5. 5 means we're going to have 5 numbers in the initial array, right? And 4 means we're going to have 1, 2, 3, 4, 4 operations on this array. So what kind of operations? Let's take a look. This is the initial array, right? And the first operation is to move 3 to the front of this array, right? So 3 is moved to the front. And the second operation is to move 5 to the front. 5 to the front. The rest of the array is staying the same, right? And the third operation is to move 1 to the front. The fourth is to move 4 to the front, right? So that is the input, right? So what's the output here? Output is the for each number, what's the leftmost position of that number and what's the rightmost position of that number, right? So let's see, we got ones here, 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 and here, 5 ones, right? So the leftmost position is 1, right? And the rightmost position is 3. So we output 1 and 3. And what about the 2? So 2 is here, 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 and here. So leftmost position is 2 and the rightmost position is 5, right? So we output 2 and 5 here. So let's take the last example, 5, right? 5 is here, 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 and here. So the leftmost position is 1. Rightmost position is 5. So we output 1 and 5, right? So that's the meaning of output. So how do we solve this problem? So we are going to do this using a very interesting method. So we have a initial array, right? So we can put this array at some place, like this place, right? And we make sure there is plenty of space here that we can move the number to those places, right? So we got 4 operations. So we make sure that the empty places are bigger than 4, right? So whenever we are going to move a number, we are going to remove it from the initial array and then put it to the front, right? So the second array we are going to have is like this, right? So 3 is moved to the front of the array, right? We can just ignore the empty space here, right? Because they don't matter. So as long as we know the relative position of these numbers, so it doesn't matter that we got a lot of blanks here, right? So what about the third operation? So we are going to move 5 to the front, right? And the rest of the array stay the same, right? Like this. So 5, 3, 1, 2, 4. 5, 3, 1, 2, 4. The same array as this one, right? But it has a lot of blanks. So why do we do this? So in this way, we can take advantage of binary index tree, right? So if you do not know how to use binary index tree, I suggest you watch some tutorials about that before we move on. So I'll post a link below the video, so you can check out the link and learn the implementation of a binary index tree, right? So binary index tree's function is basically just one function. It is to query the array's suffix prefix sum, right? For example, if we have an array like this, right? Uh, we want to query the prefix sum in a log n manner, right? So let's say we want to query the prefix sum of 2, then the output should be 2 because 1 plus 1 equals 2, right? So let's say we want to query the sum of prefix sum of 4, then the output should be 3, right? So 3 ones here, right? So that is the binary index tree. So what we do about the binary index tree here? So let's say we can replace. So we want to query very fast that what's the position of an arbitrary number in the array, right? So for example, we want to query the position of 2 in this array. So we can replace all these numbers to 1, right? In this way, what's the position of 2? We just need to query the prefix sum of 2, right? So its position is 4 because the prefix sum is 1 plus 1 plus 1 plus 1 equals 4. So in this way, we can get an arbitrary numbers position very easily, right? So with that being said, let's look at the algorithm here. So first, we are going to use LX to record the leftmost position of X, right? So for example, LX1 equals 1, right? And on the contrary, Rx means the rightmost position of X, right? For example, R1 equals 3, right? So LX and RX record the mean and the max position for each number, and their initial value is X, right? Because they start from X, so their initial value is X, and then we will update it during the iteration of operations, right? So for each operation, we are going to update Rx to last X position, the maximum number of the last X position and the current Rx, right? Because if the X position is bigger than current Rx, then we need to replace Rx with the bigger value, right? Because the rightmost position is the maximal value, right? And then we are going to set Lx to 1 because there is no more positions to the left of 1, right? So we just update it to 1. So I want to revisit last X position here. What does that mean? So we look at the real example here, right? So so for the first operation, here is the first operation, right? It's 3. So we are going to check the last position of 3, which is here. Its location is 3, right? Because the prefix sum between this range is 3, right? So the last x position is 3, and it equals to current Rx. Current R3 equals to 3. So the Rx remains 3 here, right? And let's take another example. So in the second operation, we move 5, right? And what's the last position of 5? It's here, right? So the prefix sum of this part is 1, 2, 3, 4, 5. 5, right? So we replace the R5 equals maximal 5, 5, right? And we replace um, 5, L5 equals 1, right? Because the leftmost position of 5, of course, is 1, as we can see here, right? So let's move on. So the third operation is to move 1. So what's the 1's last position? It's here, right? So what's the prefix sum of this part? It's 3, right? So 1 is previously at 3. So R1 equals the maximal 3 1, right? R1 previously is equal to 1, right? So as we can see, we find the rightmost position of 1 now is 3, right? So we update it and put L1 equals 1, right? And the last operation is to move 4. So what's the last position of 4? It's here, right? And we query the prefix sum. What's the prefix sum of this part? It's 5, right? So we updated R4 with 5, right? So we got another 5 here. And L4 equals to 1, right? And then it's not end yet. After we see, after we 1 second. After we make all the updates for the operations, we are going to calculate the current position of each x, right? Because we haven't moved a number yet, so that number may be at the rightmost position. so we need to update the current position with Rx. I mean, we need to update Rx with the X's current position, right? So for example, where is 4 now? 4 is the first of the array, so we update it. But 1 is less than 5, so it doesn't have any effect, right? And we check where is 1, so we check the prefix sum of this part, right? So it's 2, so we use 2 to update it, to update R1. So what's the position of 5? So the prefix sum is 3. So we use 3 to update R5, right? Etc. So that is our way to solve this problem. So with that being said, let's look at the code. Okay, here is the code. So this part is the implementation of binary search, binary index tree, right? You can just copy paste the code to your template, right? So you can use it very easily in the future, right? It only has two methods. One is update. So let's say you have an array like this. Update PLS. Let's say you want to update it 3 with value 1, right? So you want to put this 0, replace this 0 with 1, right? So you run the update here. And query is just to return the prefix sum of for the range from 1 to position, right? So for example, you want to calculate the prefix sum of 3. You will run this method and it will return 2, right? Because the sum of 1 plus 1 plus 0 equals to 2, right? Very easy. And this part is our main part. First, we are going to initialize all the Li and Ri, right? And this part, AI, is where we save the current position of I, right? So, so the current, we place a not of blank before the initial array, right? Don't forget about the blanks, right? So the current position of these guys is m plus I, right? M is the size of the created blanks, right? And then we will update the binary index tree to this fashion, right? And then we will iterate through each operation. And for each operation, we will update the L and update R by using the binary index tree, right? And we are going to update the binary index tree because when you move a number, for example, you move 2 to this place, you will update the current binary index tree, right? Because you minus 1 at this position and plus 1 at this position, right? So you need to update the binary index tree here. And AT still keep record of the current T's position, right? And we need to remove one number and add one number, right? And in the end, you are going to calculate, you are going to update Ri with each the last position, the current position of I, right? And then you can output the answer. Cool. I guess that's it for today. Thank you for watching.